Hey everyone, welcome to the final video in our measurement and geometry series. Now, we looked in the previous video at the sphere. We started looking at this particular 3D shape and we looked at the surface area of it. 3, 2, 1. Hey everyone, welcome to the final video in our Year 10 measurement and geometry series. In the previous video, we started to look at this really special, weird 3D shape known as the sphere. And we looked at its surface area and how to use that in calculations. Now today, we are going to talk about volume. So, the sphere, as we said previously, is a really weird shape, in the sense that if you think about how we dealt with volume for prisms or other shapes, take something like a cylinder, for example, one of these weirder shapes we did. All of the shapes we've looked at for volume, other than pyramids, they had a consistent cross-sectional area. They had this area that went all the way through the shape, top and bottom and all the way through. What's weird about the sphere is that it has the same cross section. So like if you were to slice the sphere here, for example, it would have the cross section of a circle there. But if we sliced it somewhere else, say up here, then yeah, we'd have a circle, but it would be actually a lot bigger. So there's actually no real nice way to think about working with this particular thing. But a lot of these ideas about the volume of a sphere, and spheres in particular, can be attributed to one of the great mathematicians, Archimedes. We've talked about him before. And in the next couple of examples, I'm going to show you the different ways that we can come up with a formula for the volume of a sphere using the volumes of some other shapes that we know. We've done this many times when we looked at measurements, particularly with area. If you remember, we looked at breaking apart and making new shapes to tell us about these new areas. We were always able to relate these to new shapes. Now we're going to be doing the exact same thing with the sphere. Now, as I've said before, this next explanation is really for the people that care and sort of want to figure out why this isn't just some arbitrary formula, how this actually works. Feel free to watch this. If you don't want to, that's okay. Just scroll through to the end of the video where we actually look at some examples, if you want to just look at applying something like this. But when we talk about the volume of a sphere, it has a special relationship with a cylinder of the same dimensions. So one of the relationships Archimedes observed was there was a particular ratio between the volume of a sphere and the volume of a cylinder here. So this inside capacity, the amount of space that fills up these two shapes. And what he came up with was that there is a ratio between these two of 2/3, or 2/3. So in essence, the volume of a sphere makes up 2/3 of the volume of a cylinder. And I might do a video later on in the future where we can actually look at filling these shapes with liquid and looking to see if this observation was in fact true. But essentially, there is a relationship between the volume of a sphere and the volume of a cylinder. Now, this is true in the case that they have the same height here. So they both have the same height h and the same radius r. So going from the middle out to some end and the middle out to some end here. So this proof, and the only way we can relate volumes of spheres to cylinders, is if they have the same dimensions, that is the same height and the same radius. Now let's actually take a moment to write this down and work through it mathematically, because it's still not really immediately obvious how we can come up with the volume of a sphere from this. But let's just write down what we know. So we know that the volume of a sphere equals to 2/3 times the volume of a cylinder. Now we've learnt previously that the volume of a cylinder is pi r squared, so this cross-sectional area multiplied by the height, the dimension going away from that. So that's times h here. Now, some of you may be looking at your textbook and going, well, I don't get it. How does this even relate? Because the volume formula that's given to me in my textbook is volume is 4/3 pi r cubed. And when I saw this volume for this formula for the volume of a sphere, you think, how do we even get these numbers even? Where does my cubed come from? Where does this 4/3 come from? We're going to show how that works right here. Now, you may notice that from that formula I wrote before, let me actually keep it here, volume equals 4/3 pi r cubed, you're probably thinking, well, what's the deal with this h? How do I get rid of the h? Now this is where it takes a little bit of creativity and a bit of manipulation and understanding of the concepts of spheres and circles and things like that. Now, we have that these two heights are identical. So the length from here to here is equal to the length of here to here. So we want to write the height in terms of something we know about this circle, or this sphere, I should say. Now, a sphere is the same no matter what orientation we put it in. We can rotate it around, do anything, and it'll always have the same height. And the height actually ends up being pretty specific, because if I measured from the bottom here all the way to the top and drew a line through the center of my circle, my circular face of my sphere, I should say, well, this is just the circle's diameter, right? Anytime we measure from the one end to the other end of a circle and draw a line going through the middle, that is the circle's diameter. So we can write the diameter as, well, 2 lots of the radius. So this height is the same as the diameter, which is the same as this height. So therefore, we can substitute this 2r in for the h, because the height of both is just equal to the diameter of a sphere. The diameter of a sphere is still just its height, which we can give as 2r. So instead of putting h here, we are going to put 2r. So I'm going to write that in the next line of working. So we have 2/3 times pi r squared times 2r. Okay, now if I multiply this all together, then, well, let's group everything together in a nice place. So I'm going to put all the numbers together. So 2/3 times 2 times pi r squared times r. Okay, so if I multiply 2/3 by 2, well, I can think of this as just a fraction, 2/1. So I'm going to multiply the numerators and I'm going to multiply the denominators. So 2 times 2 gives me 4. 3 times 1 gives me 3. Or if you just take a fraction of a quantity, you'll get 4/3 in the same way. And I still have my pi, that doesn't change. But here I have r squared times r, or times r to the power of 1. So if I multiply numbers with the same base, so r and r here, I'm going to add the powers. This is going back to what we learned from indices. So r squared times r, or times r to the power of 1, gives me r to the power of 3. So we arrive at an expression for the volume down the bottom, which is exactly the same as the expression that you guys would probably have seen in your textbooks. So this is one way we can think about the volume of a sphere. But there's actually another relationship between the volume of a sphere and some other shape. So if you were to do this at home, if you had access to something like this, you filled them with water, you would also notice, as Archimedes did, that the volume of a sphere is also equal to 2 cones with the same dimensions. So if I had the same height of this sphere, h, as each of these cones, h, and the same radius as well, same radius, all of these have identical radii. Now, we can prove this in the exact same way. I know that if I put 2 cones, if I fill those with water, it will fill out the space. So the space in here will fill out the space in my sphere perfectly, if these are the same radius and height. So let's have a go at doing a little bit more of this mathematical manipulation and see if we can get to the same formula we established up here. Now, I have that the volume of my sphere is going to be 2 cones added together, or 2 cones multiplied by 2. But I'm just going to add them together, do it the long way. So what's the volume of a cone? Well, we learned that cones have 1/3 of the volume of a cylinder. So this is going to be pi r squared h divided by 3 plus pi r squared h divided by 3. Okay, so notice here I'm adding this identical thing with this identical thing. So this is like saying, well, pi r squared h plus pi r squared h all over 3. Because when we add fractions, as long as we have the same denominator, we can just add the numerators. But to write this in a short way, when I'm writing the same number added by itself, even if we don't know what pi r squared h is, if I add 2 of the same number, I can just write that as 2 lots of that number. So I'm going to write that as 2 pi r squared h. Now, this would be the same if the pi r squared h is a little weird to you. Imagine this was just a regular algebra question with x and x. If you added x with x, you would get 2x. The same with 2 lots of x. The same way if you added 4 with 4, that's the same as just going, it gives you 8, that's the same as just writing 2 lots of 4. And that's what we've done here with pi r squared h. Okay, so we've got that multiplication happening on the top, and we have this denominator of 3. And in the same way, as we said before, the height of all of these is going to be the same as just the diameter of the sphere. So 2 times its radius. So what we can do here, once again, we can substitute this h, we can substitute in for this h, my 2r. So I get 2 pi r squared times 2r over 3. And then you can hopefully see already, I'm going to get to the same answer. 2 times 2 gives me 4, and pi r squared times r gives me r cubed. It gives me pi r cubed, I should say, and we have a 3 on the denominator. We came up with the same volume expression using 2 relationships that the sphere has with other solids. A relationship between 2 cones getting added together, and the volume being 2/3 of the volume of a cylinder. So that's the backstory, right? This is why this formula that you're probably seeing in your textbooks, it's not just some arbitrary numbers, which I actually kind of thought when I was in school as well. This was never really shown to me. But if you're interested now in just using this, let's jump straight into some questions. Okay, so we want to find the volume of a sphere with radius 7 centimeters. Well, now it's just a matter of substituting the important bits into our equation. So we know the volume of a sphere is going to be pi r cubed, 4 pi r cubed over 3, just like we established here and here. And now, it's important to note that having it as 4 over 3 times pi r cubed, that's the same as just having 4 pi r cubed over 3. It means the same thing. Because if I were to multiply these together, and this is important just to talk about, if I'm to multiply pi r cubed by 4 and 3, I can write pi r cubed as pi r cubed over 1. Multiply the top gives me 4 pi r cubed. Multiply the bottom gives me 3. So it essentially gives me the same thing as I have here. Just a little side note, if anyone was looking at that and found it a bit confusing. You can write it in both ways. Okay, so now we just want to substitute our radius into here. So we get left with 4 pi times 7 cubed over 3. And when I get my answer, when I put that into my calculator to 2 decimal places, that gives me 1,436.76 centimeters cubed. This is correct to 2 decimal places. Okay, let's try one more. We want to find, in this question, the radius of a sphere which has a volume of 10 meters cubed. And we want to find this to 2 decimal places. So we want to find this radius r here, r meters. Okay, so what do we know? Well, we know that the formula for the volume of a sphere is given by 4 pi cubed over 3. And I'm already given its final volume of 10 meters cubed. So I want, whoops, I forgot an r here, r cubed. And these volumes are the same. So I can set my formula bit, my 4 pi r cubed, to equal 10 in order to try to think about how to solve this equation. So I get that 4 pi r cubed over 3 equals to 10. And now I just want to solve this. Now I'm getting to my r at the very end, so I just want to get rid of everything around r. So I have this whole expression on the top getting divided by 3, and that gives me 10. So that expression should be 3 lots of 10. I get that by timesing 3 to both sides. So that gives me 4 pi r cubed equals to 30. And now I can just divide, just to get my r on its own, I can just divide both sides by 4 pi. I can do this one by one as well. I can go divide by 4 first, then divide by pi. But it's a bit more time efficient to just, right off the bat, we know they're a product, just divide by 4 pi off the bat. So I get r cubed left on this left-hand side, and I get 30 over 4 pi on the right. And now here, I have a number cubed, and that gives me my answer on the right-hand side. So, To undo cubing a number, that's like saying r times r times r. Some number times itself again gives me 30 over 4 pi. And to undo this, I'm going to do a similar thing to what we did in the last video with the square root, but I'm going to take the cubed root of both sides. The cubed root is just going to give me what this value of r is. What times by itself once and then another time to give me r cubed. That's the essence of rooting numbers. So if I do that, I get r on its own, and I get the cubed root of 30 over 4 pi. And that gives me a radius of approximately 1.34 meters, correct to 2 decimal places. But that brings us to the end of the video. This is how we can use our formula to solve a bunch of different problems, either doing a bit of rearranging and solving an equation to find the radius when given a volume, or to just substitute a radius straight in to get an expression for the volume of a cylinder. Oh, sorry, not a cylinder, of a sphere. And we talked about before, just a quick recap about the different relationships the sphere has to my two cones and the cylinder, and how we can work through these to get to our formula here. But that brings us to the end of this video and this series. Thank you so much for watching, and I will see you in the next one.